So welcome everyone to our second to last code seminar this semester. Our speaker today is Ioannis, who I know from Cambridge, and he was doing his PhD there. And now he's where he was doing finite model theory with Anuj Dawar, and now he's in Oxford with Standa Živny doing some work on CSPs, which he will not talk about today. It is yours.
So many thanks to Thomas for hosting me this week. Thanks to everybody for being here. Yeah, I'll be talking mostly about some work that came out of, I guess, my thesis. And it's meant to be a really, I guess, a watered down introductory talk. So please, if you have any questions at any point, feel free to stop me and ask anything. But hopefully I'll try to make them understandable. By the end, we'll see. Yeah. So just before starting, maybe let me give like a brief overview of the picture I'm trying to paint, which is that, okay, we know that like the point of complexity theory is to somehow measure sort of classify different computational tasks according to how inherently difficult they are. But as it turns out, the complexity is maybe not so much hidden on the problem itself, but maybe on the type of inputs that we allow to certain problems. So perhaps problems that are classically known to be hard, if we restrict them onto the space of admissible inputs into those that maybe have some nice, tame structural features, then perhaps these features can be somewhat like leveraged to actually come up with efficient solutions for these problems. And somehow the goal is that we want to identify what kind of structural properties they guarantee this idea. They guarantee some sort of tractability and somehow separate them, maybe come up with nice dividing lines that separate them from the sort of structural features that necessitate some sort of algorithmic hardness. Now, traditionally, for problems that involve graphs, which is what I'll be talking about, this is undertaken by a field of graph theory called structural graph theory. Somehow the point is that we measure the structural complexity of graphs according to like whether we can decompose them in nice enough ways and then use these decompositions in maybe some nice kind of divide and conquer approach. But the thing is that we're not just interested in, say, ad hoc results that apply to maybe concrete problems one by one. We're interested in some sort of uniformity in these results. So some sort of structure that guarantees tractability for wide collections of problems. And typically we look at problems that are definable in some sort of logic. So let me start maybe with some very simple example of like three-colorability. You know this, I give you a graph. I want to test whether the graph is three-colorable. So somehow like I can color the vertices with the property that adjacent things get different colors. This is a hard problem. Complexity tells us that it is NP-complete. So no polynomial time algorithm is known to exist. Okay, very classic also textbook problem is independent set. I give you a graph and I give you an integer as well. And I want you to check whether the graph has an independent set of that size given by the integer, by which I mean collection of vertices of this size with the property that no two of them are adjacent. So like the blue vertices, perhaps if you can discern the colors here. Okay, and again, this is a very hard problem. So it is NP-complete. But so the question going back to what I was saying, what if we relativize these problems to graphs that maybe have some nicer tame features and not just arbitrary graphs? And a standard sort of algorithms course, first-year algorithms course, will tell you that independent set can actually be solved in linear time on trees. Okay, and this is the idea is like a dynamic programming algorithm, somewhat like I compute what happens in each subtree and I propagate the solution upwards. Okay, and maybe pictorially this would look something like that. So somehow I figure out what happens in each one of the leaves. With and without it, I find the maximum independent set, and I want to propagate this information upwards to the root of my tree until I get a global solution. And okay, a natural question is, could we generalize this idea of propagating information upwards to wider collections of graphs? Okay, and perhaps a natural way of doing this is to somehow measure the tree likeness of a graph. And one way of doing this is given by what is known as tree width. So a tree decomposition of a graph essentially consists of somehow a way of structuring, maybe squinting our eyes in a certain way so as to perhaps view our graph as in a tree-like way. So somehow we want to decompose it into a tree with the property that its nodes will be labeled by collections of vertices of my graph. with the property that every vertex is contained in a bag, so in one of these things. Every edge is contained in a bag, like the edge fg in this graph here has to be in one of these bags, so here. And also we want the property that this is somehow connected, in the sense that if I look for every vertex of my original graph here, if I look at the set of bags that contain a certain vertex, say G, then it has to be a contained a connected subtree of my sort of tree decomposition here. So say here I have a B, here I have a B as well. This means that the unique path between these two must all have B's inside. Okay. And somehow the way that we measure the tree likeness of a graph is by counting the maximum size of a bag in such a decomposition, and this is what we call tree width. Okay. Now, perhaps all of you know these things, but yeah, trees are precisely the graphs of tree width 1, but also things that are not tree-like, like cycles, for instance, they can have bounded tree width. But once we start looking at complete things, dense things, like maybe complete graphs, then the tree width will be n-1. You can verify that all of the things in the clique have to be contained in a single bag. But also grids, by which I mean like the graphs that look like this. Right? You can show that the tree width grows with the size of the grid. Okay. Now, with exactly the same idea that I told you before, you can, if you're given a graph and a decomposition of it, exactly the same idea as before, I can somehow propagate information from leaves to the root of the tree so as to solve maximum dependence set in time that is linear in the size of the graph. Okay, but I get some dependency coming from the tree width of my structure, of my graph. But what's nice is that also tree width is a notion that can actually be very efficiently approximated. So there exist many algorithms. For instance, you can, given a graph, you can either come up with a decomposition, like spit out a decomposition whose width might be slightly larger, but not too much, or the algorithm will decide that the tree width is actually, it exceeds what you've given the algorithm. So putting these two things together, okay, I can solve it in general, right? In linear time on any input, and I get some dependency coming on the tree width, but it's linear on the size of the graph. And exactly the same idea of somehow starting from leaves, propagating information upwards can be used to solve many problems on linear time on classes of bounded tree width, including independence set, clique, and many other classic problems from complexity. And yeah, morally somehow, as I was just saying, the way that this works is again some sort of dynamic programming algorithm. And my question is, can we somehow understand all of these results uniformly in a certain way? And this leads to somehow viewing these problems as perhaps expressible in a certain logic. And the analog here would be what people call MSO. So MSO is M stands for monadic, S for second order, and well, O for order. Essentially, it's a logic where I can quantify over sets of over vertices, also sets of vertices, and the rest is just standard sort of first order logic. So I can express with this thing something like three-colorability. Like for instance, I can find three sets that partition the domain of my graph, and whenever I have an edge, then I know that the two vertices of this edge cannot lie in the same bag, for instance, in the same part. Okay, and
don't you have to say that these are different sets? Oh,
technically, I'm lying. I'm not saying that they partition here. I'm just saying that every vertex lies in one of the parts. Okay. But okay, I can make it say that they partition.
Yes,
okay,
that's
sure. Yeah, and let me just say that from now onwards, by first order logic, I'll refer to MSO without the power of quantifying over sets of atoms.
We had a discussion about this last week. So.
Okay.
Exactly. Some people define first order logic as MSO without.
Yeah.
It's fun.
I'm sort of trying to present this with a certain perspective.
Yeah. Good. It connects to the last week.
Yes. Cool. Okay. And a kind of uniform way of understanding these results is seminal result due to Purcell from the 90s that says that if I give you an MSO sentence and a graph, I can decide whether that sentence is true or not in time that is linear in the size of my graph. I get some dependency coming, of course, from the tree width and coming from the quantifier rank of my formula, by which I mean the sort of number of essentially nestings of quantifiers. And I get some dependency coming from some computable function. This can grow actually quite badly. For instance, it could be even a non-elementary, not bounded by a Towers function. And in fact, there are simple collections of graphs for which this function is very wild. But okay, for now, what we know is that it's linear in the size of my graph, and that's all I care about. And you might wonder, how do you do independent set then? Because in dependent set, I need to find the size of something. Well, there's a sort of optimization version of the same thing, which is I give you a formula now, and it has a free second order variable. So for instance, the formula expressing that this set X is an independent set. And I can find actually the maximum set, given a graph, I can find the maximum set, the collection of vertices with the property that they satisfy this formula. Okay. Cool. And this result is essentially proved in exactly morally the same idea as this sort of concept of finding what happens at leaves and propagating information upwards. This is a property that was known about MSO since, in fact, the 1950s due to Pfefferman and Bott, and people often refer to it as compositionality. The idea is somehow, the way that maybe you should interpret this is that somehow, if I know what happens, I mean, logically, what happens at the leaves of my structure, then I can essentially efficiently determine what happens at the parents, essentially, and propagate this information. So more precisely, if I know which MSO formulas are true in a graph G, and I know which MSO formulas are true in a graph H, I can actually determine, of course, if there's a bounded quantifier rank, this is very, I always forget down here, which formulas are true in a disjoint union. And in fact, this is also true if G and H also share a collection of vertices, in which case here I mean the amalgamation over this collection of vertices. And exactly this idea and the tree decomposition allows essentially to determine what happens globally at my structure if I know what happens at the leaves somehow, and propagate this information upwards. Okay, but now does this explain sort of all instances of tractability and all kind of does this give a nice picture? Well, it does to a certain degree, but also it depends on what you want to be tractable. But from a different perspective, it does not, because planar graphs, which we know to somehow inherently be very nice, for instance, they have a p-time canonization algorithm. I can decide in polynomial time if two planar graphs are isomorphic or not. Independent set is already NP-complete on them. And sort of actually the issue comes precisely from grids somehow. So if I have grids, then essentially I can encode enough complexity so as to get hardness morally. And this is a canonical obstruction to this, by which I mean that due to a sort of cornerstone result in the theory of graphs minors due to Robertson and Seymour, somehow grids arise as canonical obstructions to bounded tree width. So in fact, any class that has unbounded tree width, including the class of planar graphs have unbounded tree width because grids are planar, and grids, I told you that their tree width grows with size. You will be able to find these things, these grids, if you have unbounded tree width, but not necessarily as subgraphs, but what does people call minors? So a minor is minor of a graph G is a graph H, which I can obtain by removing vertices and edges, but I'm also allowed to contract edges. Okay. So somehow, as I was telling you, planar graphs, we know them to be very nice. Somehow the picture is not captured though, but by Purcell. So we want to maybe squint our eyes on what we call easy and hard, perhaps. And this is where the viewpoint of parameterized complexity perhaps makes more sense. So yeah, the classical distinction maybe between P and NP might be too coarse. So essentially we want to assign to each instance a parameter and perhaps devise algorithms that solve the problem somehow morally if the parameter is small. Okay, and the right notion here would, rather than P, be FPT, by which I mean that it is polynomial, but only in the size of, say, my graph. The parameter here I do not care about, essentially. Somehow I just remove the dependency arising from it. So the same problem, like independence set, I can parameterize it naturally by the integer k. Okay. And this is what I guess you probably already know, but this is what is known as a W1 complete problem, meaning that essentially I cannot remove this dependency arising from the k in the exponent. Okay. But what's nice is that in fact on planar graphs, which somehow I wanted to make them a tractable instance, it turns out that this problem can be solved in time that is linear in the size of the graph, but and FPT, so I get its dependency on k. So more broadly, perhaps, the right perspective for viewing these things uniformly is what people refer to as a model checking problem. So if I fix a logic and a class of graphs, then by model checking on this class, I'm in the problem where you're given a sentence and a graph. The parameter now is the quantifier rank of the formula, and I want to decide the sentence, and I want to decide whether the sentence is true or not. Okay, and of course, if I look at sentences that are in MSO, where I'm allowed to quantify or set certain things, worst case scenario, I will get something that is exponential on the quantifier rank of my formula. In FO, where I do not get some, I can only quantify over vertices themselves. I'll get n to the number of the quantifier rank form. And Courcell's theorem can then be viewed as saying precisely that MSO model checking is fixed parameter tractable in classes of boundary. Okay. And the natural question then is to try to understand in which classes is perhaps first order model checking FPT. Okay, by which again I mean solvable in time that is polynomial in the size of the graph, and I get some dependency on the quantifier rank of the form. Now, as I was telling you, planar graphs have unbounded tree width due to grids. But what's very nice is that, in fact, if I look at planar graphs of a certain radius, then it turns out that the tree width is bounded. And this you can show actually quite simply. But it was first observed by Bonnet there. So if I look at planar graphs of radius r, the tree width is actually going to be 3r. And somehow this comes from what people in this context refer to as outer planar decompositions of planar graphs, which have been thoroughly explored in algorithmic settings. And so somehow this perhaps gives rise to the following notion, which is natural, which is somehow not measuring globally my tree width, but measuring only what happens within balls of radius r of my graph. So somehow I have a function which for every r assigns the tree width of the maximum tree width of all balls of radius r in my graph. And a question is, to what extent is this leverageable, and to what extent does this fit into the picture of first order model checking? Well, the answer is that it fits very nicely because of a property of first order logic, which is sort of the analog of this compositionality that I was telling you before, which people refer to as locality. So somehow the idea intuitively is that rather than with MSO, if I know what happens in one component and another globally, I can somehow determine what happens in the union. Here, if I know what happens locally within each ball of radius r of my graph, I can figure out what happens in the entirety of the graph, morally. Okay, more formally, what this theorem shows is that, what the theorem tells is that every first order sentence of a certain quantifier rank is equivalent to a Boolean combination of what people refer to as basic local sentences. So what these sentences do is that they say that you have a set things with the property that their balls of radius r are disjoint. So I have some x1, x2, x3, and I know that they're at distance at least 2r. So all of these balls are disjoint. And something locally happens within each one of the balls. So what I mean here is that this formula psi, all of its quantifiers have been relativized to elements within the ball of radius r. So somehow my formula says I have something going on here, and I have something going on here, and I have something going on here. Okay? So what locality tells you is that every FO sentence is equivalent to a Boolean combination of these sentences. So somehow the idea is that if I know what happens within each ball, I can determine what happens in the entirety of my graph. And the radius, this R, is actually determined by the quantifier rank of my formula. Okay? So this R that is in these basic local sentences is actually, okay, you can make this more, you can come up with better bounds, but you can bound it by 7 to the Q, where Q is the quantifier rank of the sentence. And this was a result shown by Geifman in the 70s, if I recall correctly, which was initially was a syntactic result. So literally, I take a first order sentence and I syntactically transform it into a Boolean combination of these.
It's proof, theoretic proof.
Yeah. So very, very ad hoc in a certain way, but also very, very effective, very computable. So somehow, literally, I give you the sentence, I show you how to transform it into these things. Okay. And what's nice now is that if we look at FO, we can start, it is sufficient to talk about local notions of tameness. So before, when we were talking about tree width, in fact, it turns out that on classes with bounded local tree width, like, for instance, planar graphs, you can still do FPT model checking. Okay, but also bounded degree. Okay, bounded degree like grids, for instance. If I have bounded degree, then each one of these balls has a finite size. It has like d to the r. So in fact, it has one of finitely many types. So somehow it's very easy to determine what happens locally. So people in this program, they essentially somehow try to push these results and push the boundaries of sort of classes of graphs that admit FPT FO model checking, coming with weaker and weaker notions that still admit this, including excluding a minor, locally excluding a minor, boundary expansion, and somehow this program eventually led to a notion people refer to as nowhere density, attributed mainly to Nesetril and Ossona de Mendez. So they're initially nowhere density they defined in terms of what they call in this program, which is by the way referred to as sparsity theory. They defined it in terms of what they call shallow graph minors. So somehow like a local shallow analog of the graph minors theory, Robertson and Seymour. Maybe easier definition to work with is the one here. What it says is that for every choice of radius, there exists a bound such that the R subdivided clique of order n is not a subgraph of any graph in my class. What do I mean by this? R subdivided clique of order n. I take the clique of, say, this is the clique of order 5, and every edge I subdivided in this case 3 times. Okay, so what this says is that for every choice of radius, there exists some bound such that these cliques are excluded somehow from as subgraphs of graphs from my class. Okay, and this it is somewhat telling you that at every depth, if I try to look at what happens, things are somehow sparse. That's the idea. At every choice of depth, there exists a bound on how or what sort of cliques I can find. Okay, and nowhere density somehow sits on top of this hierarchy of these increasing notions. So yeah, it will include bounded degree, excluding a minor, bounded local tree width, all of these things. And the culmination to this program was the landmark result due to Grohe, Kreutzer, and Sieberts, where they showed that on nowhere dense classes, we have FPT FO model checking, which in fact is almost linear in the size of the graph. What's very nice is that to a certain degree, this can be viewed in fact as a characterization because of the following observation. If I look at graph classes which are monotone, what do I mean by monotone? I mean closed under removal of vertices and edges. So planar graphs, for instance, I can remove vertices and edges, I'm still planar. Okay? Then somehow morally, if I have cliques and I'm allowed to remove things, then I have everything. So somehow if at a certain subdivision depth, I have arbitrarily large cliques and I'm allowed to remove edges, then I am as complex as I can be. So in fact, on monotone classes, this is a dichotomy. So if a class is monotone and not number dense, then FO model checking is as hard as on the class of all graphs, which is AW star hard. No need to define this formally. You can take this as saying that it's as hard as everything. Okay. But you might be noticing a slight discrepancy and a slight issue, which is the fact that this is a problem about logic. It's a problem about evaluating sentences, but it favors sparsity over density. Somehow cliques and independent sets are totally different. Cliques on the one side are dense, so somehow they fall outside of this dichotomy. Independent sets on the other side are sparse and they're very simple, and of course I can evaluate things trivially very nicely, but somehow I'm still looking at the same problem of evaluating first-order sentences. So the dichotomy gives me an answer for this, but doesn't give me an answer for that. So problem, I don't have a nice theory, okay? So one natural question is, what can we say about dense classes? Okay, so for instance, cliques. And is there a way to characterize tractable model checking for hereditary classes rather than monotone? And by hereditary, I mean that I'm allowed to remove vertices, but not allowed to remove edges. Okay? And somehow, the idea is I want to push this concept a bit further. Okay, so somehow I want to be able to talk about or produce well-behaved dense classes from sparse ones. And the right notion to do so is what people refer to as transductions. So a transduction consists of the following. The colors are not very bright, as you can see, but okay. It consists of two formulas, one describing the domain and one describing the edge relation, but they're allowed to talk about colors. Okay, so in these formulas, I'm allowed to use additional unary predicates outside of my graph predicate, my graph language. And what I can do is that I start with a graph, I arbitrarily color it in a way that I want. So this graph, I color it like that, and then I apply my interpretation to turn it into something that looks like it. Okay? So formally, we say that a class C is transducible in a class D if there exists a transduction, so literally a domain formula and an edge formula, and some expansion of my class D with colors, so that C, the collection of graphs from C, is a subset of the collection of graphs that I can produce in this way. Okay? So somehow I start with planar graphs, say, for instance, I'm allowed to color them in any way that I want. And then with an FO formulas, I'm allowed to produce any kind of graph that I want. And this, morally, it's sort of an analog of what happens here, right? Somehow the edge relation and the non-edge relation are sort of the same. And I want to go from, if I can say here, two things are not, whatever I can say here, I want to be able to produce here, but also using colors. Okay, and why colors? Well, somehow another issue with this problem is that you can do a lot of padding. So you can take the class of all graphs, I can pad them with a lot of independent sets, and trivially get that I have FPT model check. Okay, so I want to disallow this problem, and I actually want a notion that works well with respect to hereditariness. So somehow I want a class to be equivalent to its hereditary closure in a certain sense. So this notion, intuitively, you can think of it as saying that the class C is somehow more simple than the class D, essentially. So, and I want every class to be equivalent with its hereditary closure. So that's why intuitively, this is a collection of graphs from C, including the induced subgraphs. Okay, so intuitively, that's why I want to add these color predicates. What's interesting is that transductions can be composed. So if C is less than D and D is less than E, then C is less than E. Okay, that's easy to see. So this forms a quasi-order on the collection of all classes of finite graphs. What's a cool fun fact is that this notion also makes sense for MSO. And for MSO, in fact, the transduction faucet is conjectured to be linear. So in fact, it is conjecture that every graph class with respect to MSO is transaction equivalent to one of these. And there are structural graph-theoretic notions that would correspond. So for instance, if you're transaction equivalent to one of the trees, then you have what people call bounded shrub depth. This corresponds to having bounded linear click width. This would correspond to having bounded click width. This would correspond to having unbounded click width. Okay, this is a conjecture, and this is the part that is not known, which would also show what is known as Caesar's conjecture. But for FO, in fact, which is what we're interested in, the picture is much more wild. Okay, so it's not linear. It looks very messy. It's kind of possible. But so what we want to look at now are notions of tameness that somehow are preserved by transductions. So in other words, we want to look at transduction ideals in this faucet. Okay, there are two ways of making ideals. One is to take the upwards closure of something. The other is to exclude something. Okay, and if you look at the top, I say all graphs. Well, let's take the trivial idea, which is I want to exclude as a transduction the class of all graphs. And this is what people refer to as monadic dependence. Okay, so I say that a class is monadically dependent if it does not transduce the class of all graphs. So in other words, I know that it is somewhat not as complicated as the class of all graphs with respect to this notion of a transduction. This is, at first, it sounds like a trivial notion or like a simple notion to deal with. But it turns out that all examples that we know that somehow yield tractable behavior, they're actually monadically dependent. So bounded tree width, nowhere density, and in fact, bounded twin width as well, this more recent notion that has led to a very sort of fruitful theory as well. This leads to a natural question. Are all monadically dependent classes tractable? Let's look at the other side. So standard canonical obstruction to monadic dependence are subdivided cliques, in fact. Why? Because if I have subdivided cliques, then somehow, with the power of the transduction, I can choose which subdivision vertices to include or not include by coloring them in the way that I want, and then produce whatever I want. So somehow if I can replicate the idea of removing edges by coloring subdivision vertices that I want to exclude by different colors. Okay, so somehow subdivided cliques are a canonical obstruction. And in fact, subdivided cliques are also somewhat a canonical obstruction to hardness of model checking for hereditary classes. Precisely because if I'm hereditary, I can, same idea, I can remove these vertices and then code whatever I want. So this leads perhaps to the other side of this question, which is, are all hereditary classes that are not monadically dependent, are they intractable? So I just started with the most naive notion, which is I took this wild sort of collection of things, this wild poset, and I looked at what's above. And I said, I'm not equivalent to above, to what's on top. This gives monadic dependence. And somehow it looks like this might form a very nice dividing line. Everything that I know to be tractable is monadically dependent. Everything that I know that is hereditary and not tractable is non-monadically dependent. So this has led to what perhaps people refer to as tractability conjecture, which is that actually this is the right dividing line for FPT model checking for hereditary classes. So it says that a hereditary class of graphs is tractable, by which I mean it has FPT tractable first order model check, if and only if it is monadically dependent. Now, what's very nice is that actually known results can be viewed as restricted cases of this conjecture.
Can I have
Yeah.
Any examples of now dense classes which fall under this conjecture?
Of dense classes?
Yeah. So I mean, you said the problem is that most of the time it was all sparse.
Yeah.
So now if we look at dense classes, I don't know, bounded click or something.
Yeah.
That falls in that conjecture. Something more than that?
Twin width?
Twin width, okay.
Yeah. But also everything that you can close under transductions, it will still be within the ideal.
Yeah, I just wanted a concrete example.
Yeah, twin width.
Okay. Yeah.
But even because first order logic works like that as well, in fact, you can show that somehow if you take, people look at like maybe a locally bounded click width. or locally bounded twin width, or things like that. Again, the same notion, like for every depth of radius, the balls of radius r, they have bounded clique width. Mm-hmm. This will also be monadically dependent. Mm-hmm. Because somehow if I have nice local behavior by locality of first order logic, I have nice global behavior. Mm-hmm. Okay, but actually known results can be viewed as restricted cases of this conjecture, both on the tractability and hardness side. So for instance, for weakly sparse classes, by which I mean classes that forbid some biclique. So there exists some classes weakly sparse if there exists some bound such that the biclique of order T is excluded as a semi-induced graph. It turns out then, you can show via a Ramsey-theoretic argument that monadic dependence actually coincides to nowhere density in this case. And in fact, the obstructions that you get for nowhere density, they also lead to hardness of model checking. So somehow for hereditary weakly sparse classes, those excluding bicliques, turns out that you're tractable if and only if you're monadically dependent, if and only if you're nowhere dense. Same idea. If I look at ordered classes of graphs, but what do I mean ordered? I mean that in my vocabulary, I have a symbol for an order, which I interpret as a total order in the domain of my graph. It turns out then, again via Ramsey-theoretic argument, that monadic dependence actually is equivalent to having bounded twin width on the class. And again, it's exactly the same idea. The obstructions to twin width somehow, again, lead to hardness of model checking in the presence of an ordering. So for hereditary classes of ordered graphs, you're tractable if and only if you're monadically dependent, if and only if you have bounded twin width. Okay, so I don't have much time, but let me talk about some, I guess, of my contributions. And this is about what are known as monadically stable classes. So a class is monadically stable. Somehow it's a stronger notion than monadic dependence. The idea is that the class is somehow orderless in a certain sense. So it does not transduce the graph equivalent of a total order, which people refer to as a half graph. This is the bipartite graph with the property that AI is adjacent to Bj if and only if I is less than or equal to J. Okay, so a class is monadically stable if it does not transduce the class of all of these things of growing size. And examples, in fact, include nowhere dense classes, but also it's an ideal, so again, transductions of these as well, but classes of bounded Sharp depth and other things. And it turns out that, again, much like with weakly sparse and ordered things, if I restrict onto what people refer to as edge stable classes, I mean those that forbid some half graph as a semi-induced graph. What do I mean by semi-induced is that I forbid half graphs. I don't care what happens here and here, but I forbid this behavior within parts like that. So there's a bound such that I do not have arbitrarily large half graphs. There's a bound such that I do not have half graphs of size larger than the bound, where here and here I do not care what happens. It turns out that for these classes that exclude these things, monadic stability is actually equivalent to monadic dependence. So I cannot transduce half graphs if and only if I cannot transduce everything. Okay? And in fact, this is a notion that had already been studied in the context of infinitary model theory, even back in the 80s, by Bonnet and Seymour. So I'm giving a model-theoretic definition of what they call monadic stability. It's essentially exactly the same notion. But what they show in this work is that somehow monadic stability is an important dividing line for different structural results in model theory, including some sort of tree-like decomposition, not in the sense of tree width, but a different sort of tree-like somehow way of decomposing your structure into nice pieces. But also in terms of other things like the behavior of non-forking, somehow some notion of independence in the models of these theories, and also some kind of coding. So somehow already in the 80s, about in the context of infinitary model theory, we understood this notion relatively well. But by providing essentially a finitary or sort of an effective analog of this structure theory due to Bonnet and Seymour, and somehow combining it with the structure theory of Nesetril and Mendez, eventually we got sort of a finite and algorithmic understanding of these monadically stable classes, which led to, in fact, answering the conjecture in the restricted context of edge stability. So for hereditary edge stable classes, you're tractable if and only if you're monadically stable, if and only if you're monadically dependent. Okay, because these two notions coincide whenever you're edge stable. Okay, so let me maybe very briefly tell you how this was shown. So I'm going to wave my hands a lot, but essentially due to Guyton's locality theorem, if I want to evaluate sentences in a graph, it suffices to evaluate them within balls of bounded radius, okay, where the radius only depends on the quantifier. So somehow, I want to decompose my graphs from this class into local neighborhoods in a nice way. Okay, and I can show you an ugly definition, but I can also show you a game, which is perhaps easier to understand. And this is precisely this kind of local decomposition of my graphs. So this game is played as follows. I first of all fix a radius. So this is the R radius Flipper game on a graph. It's played by two players, Flipper and connector. Initially, the arena of my game is the entirety of my graph. And at every stage, the connector will pick one of the vertices of my graph. And now what the Flipper will do is that Flipper will pick a collection of vertices and flip it. But which I mean that she will complement the edge relation within its subset. I'm not sure if the picture is very clear, but whatever edges I have here in the subset, in the flip of my graph, I have the exact opposite. Okay? And now the arena at the next step is I look at the radius R, the ball of radius R, around this vertex once I've flipped, and I continue. Okay? And eventually Flipper will win if somehow I can get my arena to have size 1. Okay, so this is precisely what this is saying. Okay. Turns out that this gives a nice local understanding of what happens in monadically stable classes. So in fact, a class is monadically stable if and only if, for every choice of radius, there exists a bound such that Flipper can win the R radius Flipper game on every graph in my class in at most L rounds. So for every choice of radius, there exists a bound essentially on the height of these trees that will give me these local decompositions of my graphs into these neighborhoods. So that's nice, because this allows for a recursive sort of model checking algorithm by essentially looking at smaller and smaller neighborhoods of radius R. But there's a problem because I want to do this at every vertex. Okay, so somehow I know that I have a bounded height for the trees, but if I try to do this on every vertex, well, the recursion tree, the branching degree, will actually be the size of my graph. So, and this will not work out nicely. Okay, so somehow what I want to do is, instead of doing this idea at every vertex one by one, I want to group them in a nice enough way. And this is what people call neighborhood covers in this context. So somehow a neighborhood cover, or a weak neighborhood cover, is a collection of sets of radiuses with the property that each neighborhood, now here I'm defining it in terms of radius 1, but you can also get what the analog is for radius R. So what I want is that each neighborhood is within one of the clusters are the blue guys, and I want to somehow have a bound on the diameter of the blue guys, and also have control on the overlap. Okay, so I say that the cover has diameter S and overlap D if the diameter of the blue guys is S, and each vertex is contained in at most D clusters. So somehow I have control over what happens over this. And we see that a class has sparse neighborhood covers if, for every choice of epsilon, I can produce these covers with the property that the overlap is bounded by n to the epsilon. Okay, so I can make these overlaps arbitrarily small. And it turns out, actually, by using this Flipper game and assuming that I can get these covers, it turns out that I have FPT model check. And so this was a result that was known already. So if take a monadically stable graph class, assume that it does have sparse neighborhood covers, then there is an algorithm which, on input the graph in a sentence, you can decide whether the sentence is true or not in this time, okay, which is FKT. This is very big, admittedly. Why is that? This is simply assuming the existence of these covers. So somehow this result initially, it was using some LP rounding mechanism, I don't remember exactly, trying to actually approximate and find these things, assuming they exist, okay? But what they did not manage to show was whether they actually exist or not. Okay, so this was one of the key contributions of, I guess, our paper. And the way that this was shown is a slightly unorthodox one, because it went via a different route, and then maybe perhaps trying to do it directly. And this is via neighborhood complexity. So this is essentially, if people are familiar with visit density, this is essentially the same concept. So somehow, given a graph, what I want to do is I want to consider the function. This is the growth function of the set system of closed neighborhoods. Okay, it is defined as I look at collections of vertices of size n, and I look at how many subsets of this guy A I can get by looking at possible vertices and the neighborhoods that define within A. So I look at all the vertices and the subsets that they can define within A and the number of such subsets, okay, given a set of size A. So this can be at most 2 to the n, of course, okay? And if I have, and the neighborhood complexity of the class is the supremum over all graphs in the class. So if I have bounded VC dimension in the edge relation, I know that by theorem due to Sauer and Cella, I know that I'll get some polynomial bound on the neighborhood complexity of my class. It turns out actually that I can get the bound to be almost linear. So in fact, for every epsilon, there exists some k such that this is k times n to the 1 plus epsilon, which is highly not trivial. And somehow this result was shown by lifting an equivalent result from the lower dense setting and using some notion which is called 2-rank in model theory, also called branching degree in structural graph theory, I think, or branching index, sorry, to somehow start from a monadically stable class, essentially reduce it in a nice enough way by reducing this kind of branching index until you get something that is monadically stable and omits a biclic. Therefore, it's nowhere dense. Therefore, I can somehow lift the result. Anyways, waving my hands a lot. But so this was the starting point for the covers. The second point, which is here, is where the sort of unorthodoxy of this argument came, is connecting it via something from a result from the 80s, from the area of geometric range queries due to Welzel. So a Welzel order on a graph is, so, okay, given a total order on a graph, I define the crossing number of this total order to be the following. So I have perhaps, is there a, okay, yeah. I have a total order in the domain of my graph. Okay, by the crossing number of a vertex with respect to the order, I mean, I look at the minimum number of pieces that I can partition my graph into intervals with the property that each one of the intervals in my total order is homogeneous to this vertex V. And by homogeneous, I mean that either it is completely connected or completely disconnected. Okay? And it's the minimum number of pieces given this total order that I can partition it into these intervals with the property that I have this property. Now, the crossing number of an arbitrary total order is simply that I look at the crossing number with respect to a vertex over all vertices, the maximum. Okay? And what Welzel showed in the 80s is that assuming that I have some polynomial bound on the growth function of the set system of closed neighborhoods for some real d in the exponent, then I can actually compute a total order in the domain of my graph whose crossing number is bounded by something nice. And in fact, yeah, this order is universal, as in the argument gives an order and then shows that it has the right crossing number, assuming that I have this nice bound over here. The way that this was used to get the covers using neighborhood complexity is actually ends up being like a very simple, greedy idea. Okay. Somehow the idea is that assuming I have this order, I essentially look at prefixes in the order that are compact in a certain sense, so they're contained in closed neighborhoods, and I somehow add them one by one, and this will give me the right covers somehow. This is a greedy idea. It's not particularly complicated. The difficulty of getting the covers essentially lies in getting the neighborhood complexity, okay, and realizing the connection with these orders. Okay. Sorry. Okay. Yeah. So it turns out that these covers exist. They can be computed efficiently, and in fact, because the previous results somehow assume their existence and show that they can be approximated, if you just use the construction of Welzel together with a greedy argument, you get some better running time, which is okay, and to be almost 6. And on the hardness side, let me just say that essentially somehow hardness comes from identifying nice obstructions to monadic stability. How do you identify these? Usually via some sort of Ramsey results. The obstructions look like this, more or less, together with half-graphs. You don't really find these as induced things. You find these as induced things in flips. So somehow I can, if I apply a number of flips, I can find these things in my graph. Assuming that I have these things, I get hardness because the existence of these things allows me to encode whatever I want. So yeah, if you're hereditary edge stable, not monadically stable, then model checking will be as hard as in the classical graphs. And in fact, because the interpretation is existential, you can show that existential for sort of model checking will be W1 hard, and problems like induced subgraph isomorphism will also be W1 hard. Okay, maybe I will not go through the recap, but let me perhaps finish with some questions. So a question here that people are sort of looking at quite extensively, and it seems like it is highly true, but we have difficulty in proving, is a so-called specification conjecture, which posits that monadically stable graph classes are actually precisely the same as transductions of no dense classes. So somehow, if I exclude half graphs as transductions, and if I close normal density by transductions, I get the same notion. Okay, this is wide open. Another sort of direction here is extending this program to relational structures, okay, like hypergraphs or relational databases and so on. But this also seems to be a bit out of reach, because even in the sparse setting, understanding what exactly the right notion is was an open problem, which we sort of looked at and answered a few years ago. Another thing that seems to be quite fruitful is sort of trying to leverage this program and the structure side of it in problems in combinatorics, for instance, in extremal stuff, like Erdős-Hajnal or Semitic irregularity and so on. But also another thing that many people are interested in is elementary model checking, because what I mean by that is getting this function, which is in the general setting, just assuming to be computable, I can bound it by a tower function. It turns out that I need different notions of tractability for this, because even graphs of bounded degree, they do not have elementary FET model checking. So somehow people try to come up with other notions of decomposing things nice enough so that this can be made a nice function. And let me just finish with those, and thank you very much.
I wanted to ask you showed this map of nowhere, like of the transduction word, and whether it's available somewhere in readable size. So.
Of course, it is in a paper by Nesetril Ossona de Mendez, Sam Brownfield, and Sebastian Sieberts, I think, and it's called something like on the transduction quasi-order, first order transduction quasi-order, something like that. Yeah. Yeah. So monadic dependence would be, again, not transducing everything. Monadic stability is like, what is it? Here, this side. Yeah. Not transducing orders, but also notions that are transaction closed, like click with, twin with. These are all transaction closed. They're ideals. Yeah, you can also use them here.
Yes, I have a question.
Yeah.
So the edge stability, how crucial is that?
In the arguments? So
can it be removed?
I mean removing it would be solving the conjecture.
Right.
So for the hardness side, in fact, it has been removed. So now we know that for the hardness side of the conjecture, it's true. So if you're not monadically dependent and you're hereditary, you're as hard, model checking is as hard as on the classical graphs. This is due to Dreyer, Melman, and Runchik.
Something new.
Sorry?
That's something new.
Yeah, that's from like last year, I think.
Okay.
Yeah. For the tractability, for instance, we do not have a nice like game decomposition. We do not have kind of this notion of rank that works for monadic dependency in general. You can show that this, okay, for monadic stability, the characterization is that for every R I have a bound. For monadic dependence, you can show that for every R, a logarithmic bound would characterize monadic dependence, but it's not going to be constant. But this doesn't give you nice sort of recursion trees to work on and come up with nice algorithms. So we, for instance, lack a nice game. Yeah. In general, the structure side is wide open because we do not understand combinatorially, or we do not have a nice enough theory that explains combinatorially how these classes work.
When you're constructing the neighborhood cover, are you using the flipper games and some other?
No.
That's completely out of.
Yeah.
Okay.
So this black box result is what essentially gives the algorithm. Yeah. And this requires the covers and uses the decomposition. But we have no black box analog for monadic dependence.
Okay. One more question? No, then let's thank Ioannis again.